Hello students, I welcome you to the next session in electrochemistry. In this session, I will be explaining to you the relationships between three important terms, namely cell potential, equilibrium constant and Gibbs energy in connection with an electrochemical reaction. As these are all important mathematical relationships, there will be a number of problems that I will be working out. So it is advisable that you sit with a notebook and a pen. Now for the cell that is shown in the diagram, which is the galvanic cell involving zinc and copper electrodes, we can write the equation as Zn solid plus Cu2 plus aqueous giving Zn2 plus aqueous giving and Cu solid. Now when we take pure zinc and copper rods in 1 molar solution of each of its ions, we have this standard cell, and then that will be giving you an E0 cell value of 1.1 volt, 10 volt. This is the value that you can note on the voltmeter that is connected in the circuit. But as the spontaneous reaction continues and more electricity is being produced, we can observe that more of the zinc atoms would go into solution as zinc ions, increasing the concentration of the zinc ions in solution. You know that the electrode potential of any electrode changes when the concentration of its ions changes, isn't it? So as the concentration of the zinc ions in solution increases, the electrode potential of the zinc electrode also would increase. At the same time, in the copper compartment, the copper ions are getting discharged as copper atoms. So the copper ion concentration is decreasing, it's falling. The electrode potential of the copper electrode would also be falling. At one stage, the electrode potential of the anode electrode would become equal to that of the cathode electrode. The electrode potentials of the two half cells or single electrodes become equal. Now what will be the reading on the voltmeter? It should be 0 because the electrode potentials have become equal. The potential difference which is shown by the voltmeter will be 0. Now we say the cell has reached the equilibrium state. At this equilibrium state, the concentration of the copper ions, zinc ions in this compartment has reached a value which will not change anymore. So we say the concentration of these zinc ions has become constant. In the same way, the concentration of the copper ions also reaches a constant value. There won't be any more change in that. Here I would like to make it very clear that the concentration of the zinc ion in this solution is not equal to the concentration of the copper ion in the cathode compartment, but their concentrations have reached constant values. Now for the above reaction which has reached equilibrium, we can write Kc is equal to Zn2 plus by Cu2 plus. That is the equilibrium constant for a reaction which has attained the equilibrium state. Now Nernst equation can generally be written as E cell is equal to E0 cell minus 0.059 by 2 log Zn2 plus by Cu2 plus for this galvanic cell. At equilibrium, there are two changes that we can make to the above equation. The E cell is 0 here because that is the reading that we get on the voltmeter at this equilibrium state, is equal to E0 cell minus 0.059 by 2. Instead of this, I am going to write Kc, log Kc. This leads to E naught cell is equal to 0.059 by 2 log Kc. So in general we can write E naught cell is equal to 0.059 by N log Kc. N is the number of moles of ions, number of moles of electrons that are exchanged in the reaction for the cell, for the electrochemical cell. When you write equation for the cell reaction, you can easily notice how many electrons are lost and gained by the metals involved in the cell. So that will give you the value of N. This is a very useful relationship because for many reactions it is very difficult to calculate equilibrium constants. Now in this relationship you see you have E naught cell, the calculation of which is very simple because we can get the electrode potentials of the cathode and anode from the available data, and N we can obtain from the equation when we write the equation for the cell reaction, and log Kc can be log Kc, and from that equilibrium constant can be very easily calculated. Doing a few problems will make you understand and remember the mathematical relationship that you just learnt. So the first one is calculate the equilibrium constant for the reaction Al solid plus 3Ag plus aqueous giving Al3 plus aqueous plus 3Ag solid. To calculate equilibrium constant, you know you need two values, E naught cell and the value of N. E naught cell can be calculated if you know the electrode potentials of the cathode and the anode. Which is cathode here? Cathode is silver because that is the one which is gaining the electrons. So E naught cell is equal to electrode potential of silver electrode, which is 0.80 volt, minus electrode potential of the anode, that of aluminium, which is minus 1.66. So you get a value of 2.46 volt. Let us write the relationship now. E naught cell is equal to 0.059 by N. What is N here? Aluminium being a trivalent metal loses 3 electrons, and to balance the charges 3 silver ions have gained those electrons to form 3 silver atoms. So the number of electrons lost equal to number of electrons gained is equal to 3 log Kc. Substituting the value of E naught for E naught cell, let us substitute the value of 2.46, and when you calculate Kc you get a value of 125.0 for log Kc. Log Kc is equal to 125.0. So Kc has a value of 10 to the power 125. In this case it becomes very simple, can straight away write. And you know this is a very very high value. This tells us that the reaction almost goes to completion, that we can't even treat it as a reversible reaction and say calculate equilibrium constant. It goes to completion. That is why it has the equilibrium constant has a very high value. In this connection, I would like to tell you some interesting phenomena that we observe in our day-to-day life around us. We have so many silver articles at home which get tarnished over a period of time. You see a black coating on the silver articles, isn't it? Very soon the silver articles, they lose their shine and they turn black with a coating of black silver sulfide. The coating is due to formation of silver sulfide. There is a simple way of making the silver articles shine once again. You take a vessel, fill it with water and keep the silver articles immersed in water, and you can boil it with a few pieces of aluminium foil. You may be having aluminium foil at home, so you just tear it into a few pieces and put the aluminium foil pieces in the water and make it boil for a few minutes. To make the reaction faster, you can add a pinch of soda bicarb, that can be added or may not be even necessary. So if you allow it to boil for some time, you can see the silver articles again regaining their polish. They get rid of the black coating, they regain the polish. This is due to a very spontaneous reaction between the aluminium metal and the silver ion. In the presence of the aluminium metal, the silver ions from the silver sulfide, they get deposited as silver and get rid of the get deposited as the silver atom, getting rid of the sulfur atom. So AgS turns to Ag in the presence of aluminium. So that is a simple thing which you can do at home, and you will appreciate that it is due to the very spontaneous reaction between aluminium metal and silver ions. The next equation for which you have to calculate equilibrium constant is 2Cr solid plus 3Cd2 plus aqueous, giving 2Cr3 plus aqueous plus 3Cd solid. E naught of Cr3 plus bar Cr is minus 0.74 volt, and E naught of Cd2 plus bar Cd is minus 0.40 volt. One more thing that you need is the value of N. Chromium is a trivalent metal, cadmium is a divalent metal. So to balance the charges here, we have to consider the lowest common multiple of here 3 and 2, that is 6. That is how we have balanced this equation. Hence the number of electrons lost equal to the number of electrons gained is equal to 6 here. Now we can write E naught cell, which is 0.44 minus 0.74. So we have value of this minus 0.44. So we have a value of 0.34 volt. This is equal to 0.059 by 6 log Kc. When you work it out, you get for log Kc a value of 35.89. Sorry, 35.59. 35.59. I'll just teach here how to get the value of Kc, and you have values like this. This you can split as 35 plus 0.59. 35 plus 0.59. For 35 you can easily write 10 to the power 35. For 0.59 you can get the anti-log, that is 3.89. So Kc will be 3.89 into 10 to the power 35. I suppose it is clear to you. So from a value of E naught cell and value of N, which we derive from the equation, we can calculate equilibrium constant for any given equation. Another useful relationship for an electrochemical cell is that between the cell potential and Gibbs energy. As you know, in an electrochemical cell, a spontaneous reaction takes place and the chemical energy of the reaction is converted into electrical energy. If this electrical energy is allowed to do work, the free energy of the system will have a negative sign. So that will be minus del G. This minus del G is actually a measure of the useful work that can be derived from the system. It is quantitatively given by the product of the EMF of the cell and the total quantity of charge that has passed through the cell. So we can write it as del G is equal to minus NF E cell. So this is again I can say the second quantitative relationship that is going to be very useful in working out problems. Then if this cell is under standard conditions with all the solutions at unimolar concentration, we can write del G naught R for the reaction minus NF E naught cell. We can substitute for E naught cell the quantitative relationship that we learnt a little while ago, 2.303 RT by NF log Kc. So this leads us to the relationship delta G naught R is equal to minus 2.303 RT log Kc. You find the three important quantitative relationships between E naught cell, equilibrium constant and Gibbs energy of an electrochemical cell. Having learnt these relationships, we will now use them in problems. I have given you two equations for which you have to calculate del G naught. Two important data that you need for calculation of del G naught are E naught cell and the number of moles of electrons exchanged between the species. The cell E naught cell you can obtain from the given electrode potentials, and from the equation you can get the value of N. I suppose by now you are proficient to derive the value of N from the equations given for the cell reaction. I have taught you that in my earlier sessions. I suppose by now you should be familiar with that. Having done the problems, you can verify the answers. In the third problem, you are asked to calculate delta G for the given galvanic cell. How would you proceed? The first step is to write the equation for the cell reaction. After doing that, go ahead to calculate E cell using Nernst equation. Then using this E cell value and N value obtained from the equation, you can calculate del G. I advise you to refer to the solution after doing the problem yourself. The equation is Sn solid plus 2H plus aqueous giving Sn2 plus aqueous and H2 gas. The equation helps you in two ways. One is for the calculation of N value, another one for substituting the concentration correctly in the Nernst equation. See, the equation has 2H plus. Then you will remember that you will have to square the concentration of H plus in the Nernst equation. So Nernst equation is given there. You can substitute for E naught cell. For hydrogen electrode, at an electrode potential is 0. 0 minus 0.14 gives you 0.14 volt for E naught cell minus 0.059 by 2 log 0.001 by 0.002 the whole squared. That will give you 0.0295 logarithm of this. If you simplify, you will get log 500 and you will arrive at a final value of 0.06 volt. Now for del G is equal to minus NF E cell, and N you know has a value of 2 into 96,487 into the E cell value that you arrived at 0.06 volt. This will give you a value of 11.578 kilojoules. I suppose you have done the problem correctly and also have gained confidence in working out the problems using the mathematical relationships that you learnt in this lesson. I conclude my session with this. Thank you.